Okay, the next property we'll talk about, or the next set of properties we'll talk about, will be freezing point depression and boiling point elevation. So we have in this slide a normal phase diagram where we can look at how pressure and temperature affect the phase of a material. So going from solid, liquid to gas, for instance. And if we take a look at the effect of adding a solute to a liquid, we get something like this. So the curve shifts essentially down and left. Okay, and the effect that it has is that it lowers the freezing point and it raises the boiling point. So you can see the line where we go from solid to liquid has moved left and down. And again, as a result, our boiling points, where we go from liquid to gas, has also moved down. So we've lowered it. Okay, so our freezing points, they've gone up, excuse me. So they've shifted down, and the result of that is that they actually go up. So our boiling point raises, and our freezing point lowers. Okay, and the main thing we're going to be focusing on with these calculations, and we'll get into the equations in just a moment, are these delta values. So the change in freezing point and the change in boiling point. Okay, so this is what the new phase diagram would look like after we add the solute. So notice everything moves. Triple point moves, boiling point moves, everything moves. Okay, so let's take a look at what's going on. So it's very similar to vapor pressure. And here we have a equilibrium at freezing point. Okay, so we're at the freezing point of the solvent, and we're at that equilibrium. So we have molecules simultaneously becoming solid and then going back into solution. So we're right at the freezing point. So we're at the equilibrium where we're forming solid, but we're also still a liquid. So if we add a solute to this, so we have a happy equilibrium here, just like we did with our vapor pressure. So if we add a solute, we disrupt the equilibrium. Okay, so now we have these solute particles, and they're kind of in the way. Okay, so they're bumping into them, they're just basically disrupting the equilibrium. We can pretty much leave it there. And the result of this is when equilibrium is restored, now our freezing point is at a lower temperature. Okay, so our new equilibrium now lies at a lower temperature than with the pure solvent. Okay, so we're going to use a couple terms here. Pure solvent means the solvent, or the solution, not the solution, but the solvent before we've added anything. And then we'll have the solution, which is after we've added the solute. Okay, so it's sort of like our normal vapor pressure that we looked at with vapor pressure. Okay, and that's really all you have to know in terms of sort of chemically what's happening. So we're just disrupting that equilibrium, just like we did with our vapor pressure. So how do we calculate this? So to calculate the change in freezing point, and it's a very similar equation for boiling point. So we have delta Tf, so the change in the freezing temperature, is equal to a constant, so a freezing point constant, times the molality of the solution. Okay, so here now, instead of using mole fraction, we'll use molality. So delta Tf is just the change in freezing point. Kf is our freezing point constant. And of course, little m is our molality. Now, what this doesn't tell you is it doesn't tell you the new freezing point. This tells you how much the freezing point will change. Or you could also calculate this. So you can measure the temperature change and then calculate backwards with this. Maybe you're trying to determine the constant, for instance. Okay, so to calculate the new freezing point, so here we have Fp new, in other words, the new freezing point, is equal to the original freezing point minus delta T. Okay, so for instance, we know the freezing point of water is 0. If we add salt, we lower it, so we would say 0 minus, I don't know, let's say 10. Okay, so it would be minus 10 is the new freezing point. So be very careful, because don't answer the question as telling me, unless I ask you how much it will change. If I ask you for the new freezing point, make sure you do the second step. If you stop at just calculating the delta, you won't have the actual freezing point, you will just have the change in temperature. Now, it's kind of convenient for things like water where it's already 0, so essentially you can just throw a negative sign on there. Okay, but be very, very careful and make sure you understand what it is you're actually calculating. Okay, so that's freezing point. And for boiling point, we have a very similar equation. Okay, so delta T, B, so the change in boiling point is equal to KB, which is a boiling point constant, times the molality. And again, this tells us the change in temperature. So to calculate the new boiling point, this time we'll say the normal boiling point plus the change in temperature. Okay, so again, make sure you do this second step. Don't just stop after calculating the delta. Okay, just make sure you make sure you understand what it is you're calculating. Okay, so pretty easy equations, right? And here are some constants just to give you an idea. So these are things you could find in data tables. So normal boiling point of water, 100 degrees C, we know that. KB, 0.51. Normal freezing point is 0. And the KF was 1.86. These constants will be they'll be given or I'll ask you to calculate them. Most of the time they'll be given. So most of the time you'll actually be calculating little m. So you'll probably be determining the molality, and then from that you can do things like determine the molar mass and things like this. Okay. So here's a question. So what is the freezing point of a 1.7 molar or molal aqueous ethylene glycol solution? And it gives us a note. The molal freezing point constant, so the K, for water is 1.86 degrees C over molal. So notice the units here, degrees C over molal. So that will cancel everything out. Well, it will cancel out the molality anyway. Okay, so how do we do this? So first thing we need to do, calculate the change in freezing point. Okay, so we know our K value and we know our molality. So they were nice enough to give us both of those. So all we have to do, plug them in. Okay, so 1.86 times 1.7 gives us a delta T of 3.2 degrees C. So now we know how much the temperature will change. But what we need to do now is determine what the new freezing point is, because that's what they've asked us. What's the freezing point? They didn't ask us what the change in the freezing point would be. So now we have to think, okay, so if I'm doing freezing point, should it go up or should it go down? And of course, from freezing point depression, we know it should go down. And if you have any trouble remembering should it go up or should it go down, remember that when we salt the roads in the winter, well, maybe not in Texas, but in some places where they need to salt the roads in the winter to prevent ice, they're lowering the freezing point so that it has to get colder, or in other words, so that at that temperature, the water will no longer freeze. Okay, so they've lowered the freezing point, so that means at the current temperature, it won't be ice anymore, it'll actually melt. Okay, so just remember we salt the roads to make the freezing point go down, or just remember freezing point depression. So now, we want to calculate our new freezing point. We know we take 0 and we subtract the delta T, so we end up with minus 3.2 degrees C. And we can do a logic check here. Okay, so I know the freezing point should go down. I got a number below 0. Does that make sense? Yes. Okay, so make sure you do those little logic checks at the end too. Okay, so here's one for you to try. So it says, what will the freezing point of water, what will be the freezing point of water if 27.35 grams of sodium chloride is dissolved in 575 grams of water, and it tells you the KF for water is 1.86 times, or 1.86 degrees C over molal. So give this one a try. These aren't really tough, but give it a try, see what you come up with, and then we'll go over it. Okay, so let's take a look at this one. So they've asked us to calculate the freezing point of water if we add this much salt to it. So let's take a look at how to do this. So the first thing we know is that it will be this type of equation, or this type of problem. So we're just going to say, okay, a freezing times little m. Okay, so they told us we have this much water, so 575 grams, and they told us we have this much sodium chloride, so 27.35 grams. So the first thing, and they told us our KF for water is equal to 1.86 degrees C per molal. Okay, so that's everything we need from the equation. So now what do we need? We need to calculate the molality of the solution. Did they give us a molar mass? They did. So let's go ahead and copy that down to 58.4 grams per mole for sodium chloride, and that's the only molar mass we need since we're not concerned with how many moles this is of water. Okay, so little m will be equal to, well, first we need to, so let's set up what little m is. So we know it's the moles of the solute over the kilograms of the solvent. Okay, so we need to first calculate the moles of the solute. So we'll just say 27.35 grams of the solute, and our molar mass, so for every 1 mole, we have 58.4 grams. If you are new to my class and you didn't have me last semester, this is the same thing as writing this. I just want to make sure that that's clear to everyone in case your last professor didn't do this, just saying times 1 mole over 58.4. Okay, so those are the same thing. And you don't have to write it the way I do. It just makes it a lot more convenient when you start getting into longer calculations. Okay, so if we do this math, we end up with 0.468 moles. Let me just double check that. Yes, okay. And that's in moles. Okay, so now we can calculate our molality because they also give us the mass for water. So little m will be equal to 0.468 moles over, and just convert this to kilograms, 0.575 kilograms of water. Okay, so our little m will be 0.814, and those are units of molal. Okay, so now what's left is to calculate delta T. So we'll just say 1.86 degrees C per molal times 0.814 molal, and molal will cancel with molal, and our delta T will end up being 1.51 degrees C. So the question asked us, what is the freezing point? So it didn't ask us the delta, it asked us the actual freezing point, so we have to write this part now. So the freezing point will be equal to 0 degrees C minus 1.51 degrees C, which of course is just minus 1.51 degrees C. Okay, and that would be our final answer. So this last step may seem a little silly when we're dealing with water and freezing point, but when it comes to other solvents that don't have a freezing point of 0, you'll need to make sure you do this step. So go ahead and write it out just to get it in good practice. Okay, so there's your full solution for that. Okay, so here's another one for you to try. It says 0.114 grams of eugenol, and it gives you a formula and a molar mass. And it says it's the active ingredient in cloves, and it says it's dissolved in 10 grams of benzene. What is the boiling point of the solution, given that the Kb value for benzene is 2.53 degrees C per molal, and the normal boiling point of benzene is 80.10 degrees C. Okay, so it wants you to calculate the new boiling point for the solution if you add that much eugenol to that much benzene. Okay, so give this one a try. So it's very similar to the freezing point, but this time you're calculating boiling point. Okay, let's take a look at this one. So very, very similar question, but now we're calculating boiling point. So they gave us this info. So they told us we have 0.144 grams of eugenol, and I'm just going to write EUG just for simplicity. Okay, and they tell us that it has a molar mass of 164.2 grams per mole. Okay, and they tell us we have benzene, and we have 10 grams of benzene, and they tell us it has a Kb of 2.53 degrees C per molal, and a normal boiling point of 80.10 degrees C. Okay. And we know that we need our delta T equation. So delta TB is equal to our constant for boiling times our molal. So first thing we have to do, we have to convert our mass of our solute to the moles of our solute. Just the same way we did before. Grams, and then for every 1 mole, I have 164.2 grams. So this gives me 8.77 times 10 to the minus 4 moles. Let me just double check that. Yes, okay. And that is moles. Okay, we have the mass of benzene already, so we can calculate little m. So moles, remember, over kilograms of solvent. Okay, so we have 8.77 times 10 to the minus 4 moles over, so they gave us 10 grams, so in kilograms it's 0.101 kilograms, and that gives us a molal equal to 0.877. Oh, excuse me, I missed a 0 in there. Okay, so now we have our Kb, so we can just plug this in. Okay, so delta T will be equal to 2.53 degrees C per molal times our molality, which we calculated to be 0.0877 little m. Okay, and this gives me a delta T equal to 0.222 degrees C. Remember that molal will cancel here. Okay, so to calculate my new boiling point, so the boiling point of my solution will be equal to 80.10 degrees C plus, since we're going up, so we end up with a new boiling point of 80.30 degrees C, and that would be my final answer. Okay. So there's your full solution. Okay, so suppose we wanted to know the molar mass of a compound. So suppose we didn't know the identity of a solute. So we could maybe measure its mass, but we weren't necessarily sure what its molar mass was. How can we figure that out? So it says, calculate the molar mass of a compound if a solution of 12 grams dissolved in 80 grams of water freezes at minus 1.94 degrees C. So this is essentially working the problem in reverse. Okay, so how can we do this? Well, the first thing we have to do is we have to figure out what is our delta T. Okay, so remember that delta T will be equal to the freezing point minus the freezing point of the solution. Okay, so they tell us our freezing point is minus 1.94 degrees C. So to undo this, we know that our original freezing point of water is 0 degrees C, so minus a minus 1.94 degrees C gives us a delta T of 1.94 degrees C. And of course for water, that's a pretty easy calculation in your head, but when it comes to things that aren't water, you'll need to do this calculation for sure. Okay, So now we know our delta T. So what does that give us? So now we can take our equation, so our delta T equation, so delta T equal to K times M, and we want to solve for little m now, so we'll divide both sides by K, okay, just like we have here. Okay, so this would cancel, and you'd be left with m equal to the delta T over K. Okay, let's just get rid of this for now. Okay, so we have our equation solved for little m. So now we can plug in the delta T we just calculated, divided by our constant. And they didn't give us the constant here, but we know it's 1.86 degrees C per mole. Okay, so we divide those two numbers and we check our units. So delta degrees C cancels out with degrees C. And remember, if I have 1 over something on the denominator, when I flip it up, it becomes its natural form. So in other words, I end up with units of mole. Okay, so now I know the mole of the solution. Okay, but I'm not quite to where I want to be yet. So now I know the mole, but I still don't know the molar mass. So there's a couple more steps here. So what is mole, first of all? We know that the mole is the moles of the solute over the kilograms of the solvent. So I can solve for the number of moles. So if I know little m is equal to moles of the solute over the kilograms of the solvent. So if I know little m and I want to know moles, I just multiply both sides by the kilograms of the solvent, by the mass of the solvent in other words. Okay, so times, and you get the idea, but times kilograms of the solvent. And I end up solving this for moles. So as long as I know the mass of the solution, or the mass of the solvent, excuse me, then I can calculate how many moles that actually is. Okay, so I can rearrange my equation to say the moles of the solute are equal to the molality times the kilograms of the solvent. Okay, so just do that multiplication and you end up with the number of moles. Okay, but we're still not to molar mass. Now we know moles, but we don't know molar mass. But what is molar mass? So remember, molar mass is just the mass of the solute over the moles of the solute. So now we know the moles. The question tells me the mass of the solute. So now all I have to do is just calculate mass divided by the moles, and that will give me the molar mass. Okay, so if I plug those numbers in, so they told me it was 12 grams, I just calculate the number of moles here. So all I have to do is plug that in. Okay, and it turns out I have a molar mass of 144 grams per mole. Okay, so that's sort of working the problem in reverse. Okay, and there's experiments where you'll do this, so you could be given an unknown solid, for instance, and asked to calculate the molar mass this way. Okay, so here's one for you to try. So another one of those reverse kind of problems. And make sure you do understand how to do these in both directions, because I'm inclined to ask you to calculate molar mass, for instance. Okay, so it asks you a solution prepared from 1.25 grams of oil of wintergreen in 99.0 grams of benzene has a boiling point of 80.3 degrees C. So it says determine the molar mass of oil of wintergreen given that Kb for benzene is equal to 2.53 degrees C per mole. And it wants to know, it lets you know that the normal boiling point of benzene is 80.10 degrees C. Okay, so give this one a try, and then we will go over it together. Okay, let's give this one a try. So, like I said, I always like to just write out what we know first. So they told us that we have 1.25 grams, and I'm going to write O of W just for make my life a little bit easier. So oil of wintergreen. So we have that much mass, and they didn't give us a molar mass here. Okay, so we can't convert that to moles or anything like that. And they told us they gave us 99.0 grams of benzene. And they told us that the freezing point constant is 2.53 degrees C per mole. A little bit neater. Okay, and then they told us the normal boiling point for benzene is 80.10 degrees C. And they told us that the solution has a boiling point of 80.30 degrees C. Okay, and we know we're going to use our delta T equation. So K times M, this is KB. Okay, so we're looking to figure out what is the molar mass of oil of wintergreen. Okay, so the first thing we need to do, calculate delta T. So remember, delta T boiling will be equal to the normal boiling point, so I'm going to say BP naught, plus the boiling point of the solution. I'm sorry, no, I did this wrong. Plus the delta T. Got a little overzealous there. Okay, so the boiling point of the solution will be equal to the normal boiling point plus the change in boiling point. Okay, so now we want to calculate the delta T. So we'll rearrange this to say delta T B is equal to, okay, so how do we solve this? First thing we have to do, I'm going to write this out for you guys, minus delta TB from both sides. Okay, so we end up with the boiling point of the solution minus delta T B is equal to boiling point of the original solution. So that's not going to work for us. Okay, so we made a mistake. Okay, so let's try again. So we're trying to isolate delta T. So how can we do that? So instead, let's minus the boiling point of the original solution from both sides. Of course, we want to do it this way. So minus BP naught. And what does that give us? So that gives us the boiling point of the solution minus boiling point of the original is equal to delta TB. So will that work for us? That should give us our delta T. Okay, so they told us the solution had a boiling point of 80.30 degrees C minus the original boiling point, which is 80.10 degrees C, and that will give us our delta T. Okay, so if we do this, we end up with a delta T equal to 0.20 degrees C. Okay, so that's our delta T. But we're ultimately looking for our molar mass. So we can now use that along with the constant to determine our molal. So we can say that delta T is equal to KB times M. I'm going to put a line here just to help break things up a little bit. And now we can plug in our delta T. So 0.20 degrees C is equal to, and they gave us our KB, 2.53 degrees C per molal, and that's of course times our molality. So to solve for little m, we divide both sides by 2.53, and you end up with little m equal to, let's actually calculate this real quick. So 0.2 divided by 2.53, so we end up with a molality of 0.0791. And that's little m. Okay, so now, what does this tell us? So molality, remember, is moles over kilograms. Okay, so if we plug in our molality, we know that this is 0.0791 moles over 1 kilogram, or per kilogram, you could say. So how can we get rid of the kilogram part and isolate our moles? Well, they told us, and remember that's of the solvent, so that's our solvent, which is benzene. They told us we have 99 grams, so if we multiply by 0.099 kilograms, that will eliminate the kilograms and leave us with moles. Okay, so the number of moles we have will be equal to 0.0791 times 0.099. So we end up with 0.00783 moles. Okay, so we're almost done, but not quite, because remember, what are we looking for? We're actually looking for the molar mass. So now we have this value, so this is how much oil of wintergreen we added. Okay, so now we can bring that down here. So that was 1.25 grams. So our molar mass will be equal to 1.25 grams per 0.00783 moles, which gives us a molar mass of 159.84 grams per mole. Okay, and if we wanted to double check our answer, we could actually look up that value if we wanted to. Okay, so not that complicated of a problem, but it takes a lot of steps. Okay, so it's more tedious than it really is complicated. Okay, so there's your full solution, and let's head back over to the slides. Okay, so there's one small piece of this puzzle that I haven't mentioned yet, and it doesn't make it that much more complicated, but it's one more thing to consider. So one thing we need to talk about now is electrolytes. So what exactly is an electrolyte? And how does this affect our collidive properties? So one important thing is, as we mentioned at the very start of this section, we know that collidive properties only depend on the number of particles dissolved. Okay, so that means that solutions of electrolytes, which in other words break into ions, should have greater effect on the solutions or on the properties such as boiling point, freezing point, than compared to non-electrolytes, so things that don't break into ions. So here's just an example of maybe sodium chloride breaking into, of course, Cl- and Na+, okay, just as an example. Okay, so any kind of soluble salt or anything that will break into ions is an electrolyte, and the more it will dissolve, the better it breaks into ions, the stronger an electrolyte it is. And this should have a greater effect compared to things that don't break into ions. And let's take a look. So we'll just walk through this one together. And I'll show you kind of what I mean here. So it says, arrange the following aqueous solutions in order of expected freezing point from lowest to highest. Okay, so just based on that information, how would you solve this? So without getting into the part about electrolytes, what do you think we would do? Okay, so which would have lowest freezing point versus highest? So we'll start with number 1 being the lowest. Okay, in other words, it would have the greatest effect. So without looking at the electrolytes, you might say, okay, well, this has the most particles. That would be first, followed by these two would be tied, and then these two would be tied. So you might come up with a solution like that. So just based on their concentration. But if we take a look at which ones are electrolytes and how they break into ions, we'll see that that's not necessarily the case. So first we'll do this. Okay, and where did I get these numbers from? Well, so this is just a way of estimating the impact that a solute will have on a solution. Okay, so all I've done here is I've taken the number of ions and multiplied that by the concentration. So how did I get the number of ions? Well, if I'm calcium chloride, I know that it breaks into 1 calcium and 2 chlorides. Okay, so the total number of particles would be 3. So then if I multiply that by the concentration, I get sort of an effectiveness factor. That's not a real term, but you can follow me, hopefully. Okay. And if we go through and we do that for all of these, so sodium chloride breaks into Na+, Cl-, so 2, HCl, H+, Cl-, so 2. The next one, we have HC2H3O2. Okay, we don't know whether that's a salt or what it is, so we don't know if it's an acid. We're not really quite sure, so we'll just leave that as 1. Okay, and the next one's sucrose. We know that's a sugar, so it'll stay as 1. Okay, so a little bit of foreknowledge, a little bit of background knowledge is needed here to know what will break into ions and what won't. Okay, and so we end up with all of these sort of effectiveness factors. So now we can order them in a different way. So now these numbers tell us how great an impact they might have on our solution. Okay, so now let's rank these. So the first one, okay, so 0.3 is the greatest. So this would have the biggest effect on our solution. Okay, and then you can kind of follow. So 0.3 to 0.2, 0.15, 0.1, and then lastly 0.05 would have the least effect. Okay, so that's a way of just estimating the impact that a solute might have on a solution. Okay, so why is this happening? Okay, so a 1 molar solution of sodium chloride does not show twice the change in freezing point that a 1 molar solution of methanol does. Okay, so even though it has twice as many particles, it's still not double the effect. Okay, so why is that? Well, this is because what we're actually talking about is called the Hoff factor. Okay, so this is a measure of the effectiveness of the ions of a solute on impacting the properties of a solution. Okay, so ideally, something like sodium chloride would have a Hoff factor of 2. And if a question asks you, in an ideal world or assume ideal behavior, that's what you would say. So you would just assume 2. Okay, but depending on our concentration, that value goes up and down slightly. Because basically you have recombination. So a very strong solution of sodium chloride doesn't have as big an impact of a weaker solution because you constantly have sodium ions finding chloride ions and reuniting, so rebonding. Okay, so in other words, there's kind of a sweet spot here. So it actually has a greater Hoff factor when it has lower concentration. And that's because, again, there's less recombination happening. So if it's much harder for the ions to find each other, then effectively there's more particles because more of it is Na plus and more of it is Cl minus with the example of sodium chloride. Okay, so in other words, they're staying separate more often in a weaker solution. That doesn't necessarily mean that a weaker solution has a bigger impact on the freezing point. It just means that the Hoff factor is greater for a weaker solution compared to a more concentrated solution. Okay, but this value over here, this would be like in an ideal world. So ideally, in an ideal world, sodium chloride has a Hoff factor of 2. Sucrose has a Hoff factor of 1. Okay, something like potassium sulfate, Hoff factor 3, because it breaks into 3 ions. So if a question asks you, assume ideal behavior for the Hoff factor, okay, you would go with that ideal value. So how does this affect our equation? So this is the piece of the puzzle I mentioned that I didn't tell you quite yet. So all it does to the equation is our equations stay exactly the same, except one small change. So we have to add in this I value. In other words, the Hoff factor. He's represented as a lowercase I. And it's no big deal. It just adds a multiplication term. Okay, so now your equation for delta T, B, and delta T, F. So for delta T, you have KB times M times I. And you have delta TF is equal to KF times N times I. So you just have to add in one more factor. Okay, so how do we use this? Okay, so here we want to know the freezing point of a solution prepared by dissolving 7.4 grams of magnesium chloride in 110 grams of water. And it goes ahead and tells us the Hoff factor for magnesium chloride is 2.7. So if the question tells you, follow whatever they told you. But if it's asked you, if it doesn't tell you, or just says assume ideal behavior, you would have gone with 3. Okay, but since they tell us 2.7, we'll go with 2.7. So how does this affect the math? Really not a big deal. So first thing, convert the mass to moles, just like we did before. So go through the molar mass to get to moles. Next, calculate the molality, just like we did before. So the moles of the solute over the kilograms of the solvent. Okay, so remember to convert your grams of solvent to kilograms first. Okay, so that ends up with your molality. Okay, lastly, calculate the freezing point. So delta T will be equal to Kf times M times I. Okay, so we know our Kf is 1.86, and that's degrees kilograms per molal, times our molality, and then over here, this is our I value, our Hoff factor, so times 2.7. So it just adds a multiplication term. It's that easy. Okay, and I could also ask you to calculate I by itself. So I could give you delta T, I could give you K, and I could give you M and ask you to calculate I, or ask you to verify that, in other words, I could say verify that the possible identity of the solute is magnesium chloride based on the I value. So if you came up with an I value close to 3, then you'd be like, okay, yeah, that's reasonable. Okay, so our delta T in this case, 3.6 degrees C. And calculate your new freezing point. So remember to do this calculation. So the original freezing point minus the delta to get to the new freezing point. So our freezing point of this solution would be minus 3.6 degrees C. Okay, and I think this is a good place to break this video. So when we come back, we'll talk about osmosis. And one thing I did want to mention, because I didn't mention it in the beginning, but when you're talking about, we'll just stay on this slide, it's fine. When you are talking about boiling point elevation, so I mentioned remembering that we salt the streets in the winter for a freezing point. Well, when you're talking about boiling point elevation, if you ever cook spaghetti or cook pasta, and you notice sometimes people will put salt into the water. Okay, so partly you're doing that for flavor, sure. But the main reason you're doing it is so that the boiling point of the water actually increases. So you're cooking your pasta in a higher temperature boiling water. Okay, so that has a lot of effects, I'm sure. But that's the main thing that you're doing with the salt when you add it into the water. Okay, so I just wanted to give you that little anecdote. I think sometimes those kind of things help you remember what exactly, if I can't remember, wait, does boiling point go up or does it go down? If I remember, oh yeah, salting the pasta, it goes up. So hopefully that'll help a little bit. Okay, so in the next video we'll go over osmosis and we'll finish off the chapter.